This is the final lesson in the Balanced Forces Model unit. This lesson is looking at Learning Goal 3, and it will examine all 4 of the success criteria, so success criteria A through D. Our learning goal and success criteria for this lesson. I understand how to solve quantitative force problems is our learning goal. And as you will see in the success criteria, the reason this lesson is going to examine all 4 of these is because much of this we have done before. So most of this is actually review. There is very little new learning here. It's more about just learning how to put all of this stuff together as far as writing net force equations, drawing quantitative force diagrams, solving net force equations for unknowns, and using sign conventions, meaning positives and negatives correctly. So because we have worked with all this stuff separately before, I think it's pretty simple to put it all together into one lesson here. So what you'll see from this lesson is simply one problem. This whole thing is going to focus on the same scenario, and we'll just go through this problem and show how we can meet each of those success criteria for this particular scenario. So the first success criteria we can see here at the top, I can write net force equations. So here's our scenario. To lift a very heavy box, you attach a rope to the box and run it over a pulley. See the picture. You also have a friend help you by lifting on the box while you pull on the rope. The box is lifted at constant velocity. So notice our picture here. We have our box here, which is in this yellowish shade of orange. And your friend is down here below the box pushing up on it, and you've attached a rope to it. You can see the rope here tied to the box that's going over the pulley. Remember, a pulley would just be some sort of grooved wheel that you run the rope over. So you're down here pulling on the rope. So the net effect is there's a tension force pulling up on the box. So you're doing all that, and you're lifting the box with constant velocity. So the first thing we're going to do here is we're going to draw a force diagram for the box. Because once we've drawn a force diagram, then we can write a net force equation for it. So recall with our force diagram, just go ahead and draw your axes, get them labeled, X and Y, and then define your positive directions. I'm going to say up is positive, down is negative, right is positive, and left is negative. Again, if you wanted to do that differently, you could, and you'll see here later on why that's important that we define our positive directions once we get to the calculations portion of this. So the forces acting on the box. Well, there's a tension force pulling up on the box by the rope. So this whole rope system here is pulling up on the box, so Ft. And you'll notice here, because I'm going to make this quantitative eventually, I'm going to leave off the whole victim agent notation just so it doesn't get so messy. Also pulling up on the box is the push force from your friend. So you push, pull, whatever you want to call it. So I'm labeling that Fp. So notice here on our force diagram, I have 2 forces acting in the same direction on the same axis. So when that happens, we always start the vectors at the middle of the diagram, at the dot there in the middle, and then notice I can just overlay one on the other. Now I'm using different colors here, as you can see, to help differentiate between the forces. You may not have different colors, and that's perfectly fine. Just make sure that you label them clearly so that we know that there are 2 forces there, and that we have those 2 different labels: the Ft for tension, Fp for the push from the friend. Now, the fact that we're told that the box is being lifted at constant velocity tells us the forces must be balanced. So we have to have at least one force pulling down on the box to balance out these 2 forces combined. Well, that's going to be gravity, so Fg pulling down. And notice this vector here, it is longer than either of these 2 vectors individually, because these 2 vectors put together, the tension and the push force, would have to be the same length as the gravitational force. So if you kind of envision stacking these 2 vectors, if I were to move this push force, this yellow vector up here to the top of the tension, you'd see they'd be about the same length. So when you draw that, try to do the best you can to get that drawn correctly. Again, we're not going to get out a ruler and measure it, make sure it's perfect or anything, but do make it believable. And then finally, to finish up our force diagram, we need some equality marks. So these two forces, the push and the tension, are different sizes. So notice I put different marks on them. I've chosen to put a hash on the push force and a circle on the tension force, to show that those two forces added together equal the gravitational force. I will use both of those marks, notice a circle and a hash, on the gravitational force. This is the notation that we use to show that multiple forces add up to the same amount as a third force or fourth force, depending on how many forces we have. All right, so now that we have our force diagram, we can now write a net force equation. Now specifically, this question says write net force equations for each axis that includes a force. Well, on this particular example, the only forces acting on the box are vertical, okay, up and down. So in this case, I'm actually only going to need one net force equation. If we also had forces acting horizontally on the x-axis, I would need two equations, one for the x and one for the y. So in this case, I only need to write a net force equation for the y-axis. So F net y equals, now as we know, it's just the sum of all the forces. So that would be the tension force plus the push force plus the gravity force. Now the fact that this is being lifted at constant velocity tells us the forces are balanced, so all of those added together have to equal 0. So there is our net force equation for the y-axis or the vertical axis. All right, let's take a look at the next success criteria now. I can draw quantitative force diagrams. Well, we already have a force diagram. To make it quantitative, we need to put numbers with it. Now at this point, I haven't given you any information that would allow you to put numbers with it, but let's say I told you this. The box has a mass of 50 kilograms. The tension in the rope is 350 newtons. Make the force diagram quantitative. Well, now that we know the mass of the box, we can find its weight. Recall, weight is just the force of gravity that acts on an object. So I can convert my 50 kilograms into newtons. This we've been doing for a bit of time now. So if I multiply my 50 kilograms by 10 newtons per every 1 kilogram, notice kilograms cancel, that will give me 500 newtons. So the gravitational force acting on the box is 500 newtons. Now, one thing to remember here about our sign conventions, we have defined down as negative. So if you wanted to say this was a negative 500 newtons, you are welcome to do that. Typically, you won't see force diagrams written that way just because it's a bit redundant, because we can already see that down is negative. But if that helps you, and you'll see why it's important later on, we're going to need to use this number in calculation. We'll need to know that it's negative. If you put a negative sign in there to help you remember that, that is perfectly fine. Now we're also told that the tension in the rope is 350 newtons. So that I can just add to my force diagram. So notice Ft equals 350 newtons. I'm just straight up told that, no calculation to do there. All right, now we still don't know what the push force is. So you might be wondering, well, what do I do then? We're not told. Well, that's actually the next part of the question, and it hits at our last two success criteria. So notice our success criteria now. We'll look at both of the last two together here. I can solve net force equations for unknowns, and I can use sign conventions correctly. So we have our net force equation. So what we're asked to do here, determine the amount of force your friend is pushing with. So that's at Fp. Well, we already have our net force equation, the Ft plus Fp plus Fg equals 0. I'm just going to write it again over here. So here's that equation. That's our net force equation. All those forces added together equals 0. Well, we need to find Fp. So I need to solve this equation for Fp. So notice that's this success criteria here. I can solve net force equations for unknowns. Well, here our unknown is Fp. So I need to ask myself, what do I need to do to get Fp by itself? Well, the fact that net force equations, by definition, are all summations, or adding up. To get Fp by itself, I need to subtract these other two forces, Ft and Fg, so that they cancel from the left side and move to the right side. So notice I'll subtract Ft from both sides. I have to do it from both sides. I can't just subtract it from one side. As you learn from algebra, whatever you do to one side, you have to do to the other. And notice on the left side, Ft cancels, because Ft minus Ft is nothing. It's 0, so it goes away. Same thing with Fg. I will subtract FG from both sides. And again, on the left side, it cancels because FG minus FG is nothing. So notice I now have FP all by itself on the left side. So just rewriting my equation, I have FP equals, and here's where the sign conventions become really important. Notice it is minus FT minus FG. So negative FT minus FG. Those all go, all those signs, the negative signs have to stay in there. I can't just get rid of them. A very common difficulty I'll see students have is they'll forget the negative sign, especially this first one, the one out front. Because I know that's something we don't always see in our math curriculum, at least not on a consistent basis, but all those negative signs have to stay there. So now that we have our equation solved, it's just a matter of plugging in our numbers. Notice we know what FT is, we know what FG is, so I can just use those numbers over here in my equation. So FP is going to equal minus, again, don't forget your negative sign, 350 newtons. Now you might be thinking about, wait, FT is up and we said that was positive. Shouldn't that be a positive 350? Here's the thing. It's not that FT is negative. It's that the equation, just based on our algebra, says that we need to take the negative of FT. So FT is positive, and so the negative of that is negative 350 newtons minus FG. Well, here's my minus sign, negative. Now FG, because it's down, we said down was negative, that's a negative 500 newtons. So this is minus a negative 500. So you can see the importance of the sign conventions, making sure you get your negative signs in there in the correct spot, being consistent with them. So simplifying this, we know if I subtract a negative, that's the same thing as adding. So this would be negative 350 newtons plus 500 newtons is what that would be. And negative 350 plus 500 is a positive 150. So the push force is a positive 150 newtons. And I can finish up my force diagram by putting the push force equals 150 newtons here on my force diagram. All right. So we just saw one example problem that went through each of these success criteria. You might be thinking, well, geez, just one example. There's going to be a lot of stuff I haven't seen there. In some ways, you're right. But what you'll find is as you continue to practice this in the worksheet that we will do, you'll find that the scenarios, while the numbers change, and yes, you end up with forces on multiple axes, both X and Y, the basic ideas don't. Because we've done all this stuff before, I just wanted to show you that one example to let you see how it all fits together. And so if you need to, as you're working on the practice stuff on the worksheet, if you need to go back and see this example again, by all means do that. But I think you'll be able to do it pretty successfully without having to do that too often.